So we're talking about different ways to figure out what the heat of reaction, the enthalpy of a reaction is. It can be measured experimentally using calorimetry, or we can infer it, essentially estimate it through Hess's law by taking some known equations and adding them together. We can also calculate it from tabulated standard enthalpies of formation. So delta H is the change in enthalpy, and so we can define zero to be anything that's convenient. So just like with altitude, we measure altitude changes relative to sea level, we measure changes in enthalpy relative to the enthalpies of elements, pure elements, in their standard states. So we decided that the people, I wasn't involved in that, they decided to use pure elements in their standard states as the baseline, as the zero. So what is the standard state? It's the state of a material at a defined set of conditions. And those conditions are going to be different depending on whether it's a gas, a liquid, or a solid. So if the element is a gas, we're looking at a pure gas at exactly 1 atmosphere of pressure. If you have a liquid or a solid, it's going to be the pure substance in the most stable form. Some elements have more than one form, so we choose the most stable form at 1 atmosphere of pressure, and the temperature of interest, usually that's 25 degrees Celsius, which is the sort of the nominal room temperature. If you have a solution, then it's the substance in a solution with a concentration of exactly 1 mole per liter. So the standard enthalpy change is given the symbol delta H with a 0 here, and that 0 represents that it's standard states. That's the enthalpy change when all the reactants and products are in their standard states. So the standard enthalpy of formation, now adding an F to this, so we've got the enthalpy change, and 0 meaning these are standard states, and F for formation. That's the enthalpy change for the reaction which forms 1 mole of a pure compound from the constituent elements. It's also sometimes called a standard heat of formation because we use heat and enthalpy sort of interchangeably. The elements have to be in their standard states. The heat of formation for any element in its standard state is 0 because we decided it would be. So we can look heats of formation up. This is table 7.5, which is in chapter 7 of your textbook. And so this has some compounds in it and some elements. So here we have Br2 liquid. That's the standard state for bromine. It's a diatomic molecule and a liquid at room temperature. Its heat of formation is 0. Here we have bromine atoms in the gas state, and their heat of formation is higher. It's 111.9 kilojoules per mole. Because that's not the normal state. So you have to put energy into the bromine to get it to do that. Here we've got HBr, hydrogen bromide gas, and its heat of formation is negative 36.3. So when you form hydrogen bromide, energy is released. So some of these are negative, some of them are positive, and the ones that say 0, those are the elements in their standard state. So here we've got carbon, graphite, and diamond, and graphite is the most stable form, and so that's the one that's 0, and diamond is 1.88. So we look things up here, and the units are kilojoules per mole. So we can write formation reactions. So for methane is CH4. There are 2 elements involved here. There's carbon and hydrogen. So we're going to have the reactants be the elements in their standard state. So this is carbon, graphite, and here hydrogen is H2. And if we're not sure which element or which form of the element is the standard state, we go look at the table. So for carbon, here's carbon, we want this graphite form. And for hydrogen, hydrogen is a diatomic element, and so it's going to be the H2. And we write this equation so that we form 1 mole of compound. Then we can say that delta H for this reaction is the heat of formation for this compound. So for CH4, how do we know it's minus 74.6? We look it up in the table. CH4 right here, minus 74.6. So the formation reactions are always written to give 1 mole of compound. Kind of covered this already. If you're not sure what the standard state is, look in a table. The definition requires that 1 mole of compound is made, so sometimes you're going to have fractional coefficients on your reactants. The units are always going to be kilojoules per mole because the reaction is always written for 1 mole of product. So the formation reaction, that sentence doesn't make sense. The formation reaction is the reaction between the elements in the compound which are C and O. Something's missing, and I don't know what it is. But we're writing the formation reaction for carbon monoxide. So here's carbon monoxide, and we're going to be making 1 mole of that. And then we have to look at, well, what are the elements? Are carbon and oxygen. And then we have to identify what are the standard states for carbon and oxygen. So we've seen carbon already. Carbon solid graphite is the standard state. And for oxygen, it's O2 in the gas state. And for these diatomic elements, we don't really need to look at the table. It's going to be the diatomic element as a gas at room temperature. But if you're not sure, the table's there and you can look it up. So here we have the reactants, carbon and O2, making CO, and we need to balance the equation, right? Because this is not balanced. Normally we would balance this by saying, well, I've got 2 oxygens. Here I need 2 of these, and then I need 2 of those. But this needs to be 1. And so we're going to have to use a fraction. So we're going to put in 1/2 O2 so that our reaction gives us 1 mole of product. And this is different than how we balance equations most of the time. But for a formation reaction, we have to have 1 mole of product. And then this number, we look it up. So there's table 7.5. In the chapter, and then in the appendices at the end of the book, there's a much longer one that has a lot more elements and compounds in it. Yes?
Is enthalpy recorded in kilojoules?
Why is it in kilojoules rather than joules? Because most of these heats of formation are in the thousands of joules. So kilojoule is a more useful unit. Yeah. Yeah. Just to make, instead of saying 110,000 joules, it's 110 kilojoules. Okay, so write the equations for the formation of sodium chloride and lead nitrate from the elements in their standard states. Include the values of the standard heat of formation for each equation. So what we're going to do here is we're going to start with letter A. So we're going to do sodium chloride. So we're going to have some reactants, and then our product is going to be sodium chloride solid, because that's what we're asked to do, right? So that's the product, and then we have to write the elements that are present in this compound in their standard states. So sodium, what's your best guess about the standard state for sodium? A solid, right? It's a metal. We're looking at room temperature. It's probably going to be a solid. And then chlorine, diatomic element, right? So this is probably going to be Cl2 gas. And then we can go check on this. Sorry, I went the wrong way. We can go check on this, and we see chlorine in the middle there. Cl2, that's the one that's 0. And sodium, Na solid, is the one that's 0. And then we're going to need the standard heat of formation for sodium chloride, and that's listed as minus 411.2 kilojoules per mole. So I'm going to write that down. And then I need to balance the equation.
Oh, half.
Yeah, half of a Cl2. I can't put a coefficient in front of the sodium chloride. I need this to be 1. Now, if you have trouble looking at the fractions and figuring out what to do, you could balance it. Let me just show you how you might do that. You could balance it the regular way and say, well, I need 2 of these and I need 2 of those. And then, okay, now I need to get it down to 1, and so I need to divide everything by 2. And this was a 1, and I divide it by 2, and so I end up with 1/2. So that's a way to do it if you have trouble. But that's the heat of reaction, the equation for formation for sodium chloride. Yes?
So the heat of formation will always give us the answer for the products on the table.
Yes. Because when we look this up for sodium chloride on the table, we are looking up the heat of forming this from the elements in their standard states.
So I don't understand
What the negative is for? Because when sodium chloride forms, it releases energy.
and that's a number we look at.
The negative 411.2 we look up in the table. Okay, so let's do lead 2 nitrate. Oops. So our product is PbNO3 2 solid. So what elements are present in that compound? Lead, nitrogen, and oxygen. So we're going to have 3 reactants here. We're going to have lead and nitrogen and oxygen. And we need to identify what are the standard states for these elements. What do you think for nitrogen? N2 gas, right? It's a diatomic element, it's a gas at room temperature. And oxygen is going to be the same. And what about lead? Solid. There are a few elements like carbon and sulfur that have some different forms that we kind of have to be aware of. But most elements, if it's diatomic, you put a 2 on it, and for its state, you look at the periodic table on the wall. The color coding tells you what its state is at room temperature. Okay, so there are the elements. Now we need to balance the equation. So over here I've got 1 lead, and there's 1 lead, so that's nice. And in here, how many nitrogens? 2. 2 nitrogens. Cool. How many oxygens over here? 6. And so then over here I need 3 oxygens. So it's balancing equations with a twist, right? It always has to be one molecule or 1 mole for the product. And then it wants us to include the value of delta H. Well, we have to look that up. So this table doesn't have it, right? There's no lead listed there. So this is Appendix B, Standard Thermodynamic Quantities for Selected Substances. And so we can go to this one and go over here. The pointer doesn't work. Here is PbNO32. And that first column is delta HF, and so this is minus 451.9. I go to the table and I look it up. Minus 451.9, is that what it was? My short-term memory. Kilojoules per mole. But your question?
That's just how much energy is being released, right?
Yes, that is just the amount of energy released when 1 mole of lead nitrate forms from its elements in its standard state.
It's not like specific to nitrogen or oxygen.
This is specific to this compound. Yeah. Yeah, to the product. Yeah. Because the heats of formation of all of these things are 0. And so delta H for this reaction is the heat of formation of this. So there are the answers. Got them correct. So that standard heat of formation corresponds to the formation of a compound from its elements in their standard states. We get the elements making the compound, and delta H for that reaction is the standard heat of formation. So we learned that we can, if we manipulate an equation, we change delta H, right? So if I take this chemical reaction and I reverse it, I put the compound as the reactant and the element as the product, what do I do to delta H? I change the sign. So I can write this equation backwards. Compound going into elements is negative delta H. So that tells me if I have this 1 mole of this compound and I break it apart into the elements in their standard states, this is how much energy change is going to result. So if this delta H was negative, then this one becomes positive, and I have to put that energy in.
So like, for example, on the problem that we just did, the lead and versus oxygen,
Mhm.
if that were all reversed, well, if lead nitrate were breaking down, would it be positive 400?
Yes. Yeah.
Okay.
So to form a mole of lead nitrate, it releases 451, and if you're going to break it down into its elements, you have to put in 451. So again, it's like buying and selling, right? You do it one way, I get the money. We do it the other way, you get the money, right?
Is copper sulfate on there?
Is copper sulfate on there? It probably is. Yeah. So this idea allows us to calculate the enthalpy for any chemical reaction using heats of formation instead of finding chemical equations and having to manipulate them and add them together. So this is easier. So what we do here is we say, well, these are the reactants, and I'm going to imagine that I'm taking them apart into the elements in their standard states. And I can look up the heat of formation, and so I can find out the negative is how much I'm going to have to put in to do that. And then I'm going to take those pieces and make the product, and I can look up how much energy that's going to give. We can write any reaction as the sum of formation reactions or reversive formation reactions. So the bottom line here is that the standard heat of reaction is the sum of the heats of formation for the products minus the sum of the heats of reaction for the reactants. Now, if you've got 2 moles of something, then you have to multiply the H by 2. If you've got 3, you multiply by 3. So that's the concise mathematical way of stating it, which some of you are going to like, oh yeah, I know what that means. And others of you are like, what the heck is that funny squiggly thing? Yeah, if you don't recognize the math symbols there, it's okay. This means sum of, and n represents the coefficients. Let's look at an example here. So we're going to look at the combustion of methane. So methane burning in oxygen forms carbon dioxide and water. And we want to find out what is the standard heat of reaction for this equation. So here are the reactants, methane and 2 moles of oxygen. And so what we're going to do is we're going to decompose these mentally, just thinking about it, imagining. We're going to take these apart into the elements in their standard states. O2 is already in its standard state. So there's O2. And if we're going to take methane apart, it's going to form solid carbon and hydrogen gas. And we can look up how much energy that would require, because that is the reverse of the heat of formation for methane, right? Carbon plus 2 hydrogens makes methane. We can look that up in the table. The heat of formation for that is minus 74.6. So what I'm doing here is I'm saying, well, I'm taking 1 mole of methane and I'm going backwards. So I'm taking this guy, and I'm taking it apart, and so that change is a positive 74.6. And then I'm going to take these pieces and assemble them into the products. So carbon plus oxygen makes CO2. I can look up that heat of formation, minus 393.5 kilojoules. So I'm going to take one of these oxygen molecules in the carbon, and I'm going to make CO2. And that's going to release 393.5 kilojoules. And I still have the hydrogen, the other oxygen sitting here. And then hydrogen plus half an oxygen is a water molecule. And I'm doing 2 of those. So here's the heat of formation for 1 mole of water. And I multiply that by 2 because I'm making 2 moles of water. And so I had to put this much in, and I got this much out and this much out. And the difference between my original reactants and my products is this much. I add these things together. I've got some, oh, yeah, that's kind of cool. And then I've got some, what are you talking about? And I got some people that are just kind of here. It's okay. Anybody able to verbalize a question? Can I explain that again? I will try. So it's a little bit like having a business or something where you have to invest and then you get money back, right? And so this is the investment in energy. I have to put this much energy in to take this apart. And then when these come together to make the CO2 and these come together to make the H2O, then I get a payback.
Are we starting out with the C and the 2H2?
We are starting here.
Right.
We're starting right here.
So that's where we're starting. Okay.
Yeah, because that's what the reactants are. And so we're going to break that up, and that requires us to put in energy, so the energy is going up. And then when those form the products that releases energy, this much for the CO2 and this much for the 2 moles of water. And so the purple here is the difference between this and this. Maybe we could do it this way. I don't know if that's helpful. We can do this because enthalpy is a state function. So is this actually the way that this reaction occurs, that this comes apart into carbon and hydrogen and oxygen and then forms CO2 and water? No, that's not how it actually happens. That's not the mechanism of the reaction. But it doesn't matter because the change in elevation is the same whether you took a helicopter or you took path A or you took path B. It doesn't matter. The path doesn't matter, only where you start and where you end up. And so this is a convenient path because we know what the energy changes involved are. So we're taking our reactants and in our heads, we're taking them apart into elements in their standard states. This is already at its standard state, and then we're going to take the CH4 apart, and that's going to become carbon and 2 hydrogens. Then we've got elements in their standard states, and we start to put those together. We make CO2, and then we take the rest of these to make 2 waters. So this change here, making 1 mole of CO2, we can look up the energy that changes when that happens. It's the heat of formation. And here, when we're making 2 moles of water, it's the heat of formation for 1 mole of water times 2 because we did it twice. This change here, we look up the heat of formation for methane, but we're not forming methane here, we're unforming methane. And so it's negative. And then we add the pieces together. Does that help? A little bit. It's a bit much to get your mind around. Yes? Okay, so you're getting lost over here?
Yeah.
So here I've got all my building blocks. And I need to make these products. So 1 mole of carbon and 1 of the moles of oxygen will make 1 mole of CO2. And that is described by this equation, which is the heat of formation for CO2. And so when I form CO2, I get this much energy released. So I used up 1 of the oxygens and I used up the carbon, and I still have these guys left. And now I can take H2 and half of an O2 and make 1 water molecule, as described down here. But I'm going to multiply that by 2. Because I have 2 moles of hydrogen and 1 mole of oxygen, and I'm making 2 moles of water. So I take delta H and I multiply by 2.
So are we, do you think it's easier to write the ones on the bottom first to make the reactants? Do you think
So we actually don't have to write these at all. So what I'm trying to show you here is the reason behind that equation with the summation signs. And so what we can do, we're doing with Hess's law, we can take these equations and we can combine them. And I think, now that I think about it, I think that's why I left all this space on the side. So if I want to combine these reactions to make this reaction, I'm going to need CH4 goes to carbon plus 2 hydrogens. And that's going to be the negative of this. So I took this equation, I wrote it backwards. And so that's going to be plus 74.6. And then I'm going to need carbon plus O2 to make CO2. And that is this one just as written. So minus 393.5. And then I need this one twice. 2H2 plus O2 make 2H2O. And that is 2 times negative 241.8. And if I add these equations together, the carbons get made and used up. The hydrogens get made and used up. And I've got, at the end, CH4 plus 2O2 making CO2 plus 2H2O. The O2s do not get canceled out.
Because they're not on.
They're on the same side. Yeah, so they add up.
So you're just making, so you're using, not really, above for that, right? So that's what you're using.
This is the equation I'm trying to make. And I can use these equations, these reactions, that I know delta H for, and put these equations together in a way that they will add up to the desired equation. This is what we were doing for Hess's law last week. And then I manipulate delta H based on what I did to the equation, and I add them up, and I'm going to get the same result. So this is what we're doing. It's Hess's law, but because we're using heats of formation, we can actually do it without looking at the equations, without adding up stuff like that. We can do it simply by doing it this way. So we can say that, well, delta H is the heats of formation for the products. Those are the things I'm making, right? So the heat of formation for CO2 is minus 393.5, and I'm making 2 water molecules, so 2 times the heat of formation for water. Those are my products. And then I'm going to subtract the heats of formation for the reactants. So minus the heat of formation for methane, minus 74.6, plus the heat of formation, plus 2 times the heat of formation for oxygen, which is 0. You're always going to subtract the reactants because the reactants are getting taken apart. So it's the opposite of the heat of formation reaction. And these, we're using the formation reaction. Any questions? I think I've got a real example coming here. The thermite reaction in which powdered aluminum reacts with iron oxide is highly exothermic. It's really, really neat. Use standard enthalpies of formation to find the standard heat of reaction for the thermite reaction. So I want the standard heat of reaction. I'm going to take the standard heats of formation of the products. So I've got the standard heat of formation for aluminum oxide plus the standard heat of formation, for iron. That one's times 2 because there's 2 of those. And then I'm going to subtract the heats of formation for the reactants, 2 times the heat of formation for aluminum, plus the heat of formation for Fe2O3. So how much energy to form this, how much energy to form 2 moles of this, and then I'm subtracting these because I'm unforming them. So if it makes more sense to you to add the negative instead of subtracting, it's the same difference, right? It comes out the same. So I'm going to subtract how much it costs to make 2 aluminums and 1 of these. That's the idea. And so I have to go look these up. And I have to remember, where did I put those in the slide? No. Nothing convenient. It's back here. So I'm going to write these on the board because my short-term memory sucks. So we've got Fe2O3 minus 824.2. And then we had Al2O3 minus 1675. 0.7. So now we can go back to this. So I've looked these things up. The heat of formation for Al2O3 is negative 1,675.7 kilojoules per mole. What's the heat of formation for Fe, solid? It's 0. It's an element in a standard state. And if you don't remember that, you can go find it in the table. It's listed there, Fe, solid, 0. So plus 2 times 0. And then I'm going to subtract here 2 times the heat of formation for aluminum. Again, that's an element. So that's 0. Plus the heat of formation for Fe2O3. So I looked that one up. It's minus 824.2. So your calculator can handle this mess. I'm going to put in negative 1675.7. 0 doesn't matter, right? And then I'm going to subtract, and the 2 times 0 doesn't matter. I'm going to subtract negative 824.2, and I get minus 851.5. And the unit on that would be kilojoules per mole. Yes?
Product side.
Mm-hmm.
Why is one delta HP and the other delta H?
Because it's a sloppy F. That's why.
Oh,
The P is in F, yes.
okay,
This
and that's
is not,
bond or something.
yeah, no.
Sorry.
There's a fat marker and small. But thank you for asking, because that would be confusing. Anything else? Any other questions? Yeah.
So why isn't the iron oxide positive?
Why isn't the iron oxide positive? Well, essentially it is, because here I'm subtracting this, and so that is the changing of the sign. Right? Personally, I like to think of, well, I'm going to heat of formation of this, change its sign, heat of formation of that, change its sign, heat of formation of this, leave it alone, heat of formation of that, leave it alone. Same thing.
We don't have to change the signs. Right?
If you're subtracting, the subtracting takes care of changing the signs. Yeah. It's just kind of how you think about it. Minus 851.5 kilojoules. There's another one. Chemical hand warmers produce heat when they are removed from the airtight plastic wrappers. Reaction is between iron and oxygen. Calculate the delta H, standard heat of reaction, and calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. Well, the first thing we have to do is find delta H for this reaction, and it's the standard heat of reaction. So that's the heats of reaction, the heats of formation for the products minus the heats of formation for the reactants. So the product, I've got 2 times the heat of formation for the Fe2O3, and that's the only product. And then I'm going to subtract the heats of formation for the reactants, 4 times the heat of formation for Fe, and 3 times the heat of formation for O2. But what about those reactants? Those are elements, right? They're not compounds? Are they in their standard states? Yeah, they are. So this is actually 0 because it's an element in standard state. And this is 0. We can look those up and put those in there and take, subtract 4 times 0 and subtract 3 times 0. And then, so what we really need here is 2 times the heat of formation for Fe2O3, which conveniently I still have on the board from the previous example. So this equals 2 times negative 824.2. And really what's happening with the units here is that this is 2 moles in kilojoules per mole. And so the heat of reaction here is 2 times negative 824.2, which is minus 1648.4 kilojoules for the reaction as written. Yes. Well, we haven't gotten to the 15 grams yet. Yeah. So we just finished calculate the heat of reaction and calculate how much heat produced when this thing reacts with 15 grams of iron. So that is stoichiometry with energy. When 2 moles of iron oxide is formed, it releases this much energy. And so our regular stoichiometry, grams to moles to moles to grams. We have a mass of iron. We have 15 grams. So 15 grams of iron. And then we're trying to figure out how much energy is released. So we're going to go grams to moles and directly to kilojoules. We don't need those guys. So 15 grams of iron times, we're going to convert this to moles. And then we use that heat of reaction, gives us the relationship between kilojoules and moles of iron. So this is minus 1648.4 kilojoules per 4 moles of iron. Because it's this one, 4 moles of iron. And then the molar mass of iron, 55.85 grams. And so our units are working out 15 divided by 55.85 times negative 1648.4. Don't forget the divide by 4. And so I'm getting negative 110.7 kilojoules. Actually, it'd be negative 111 kilojoules, 3 sig figs. Now, if this was a master in chemistry question and I typed this in, would it like the answer minus 111? No. Because this is saying how much heat is produced. Minus 111 is produced. No, 111 is produced. The minus tells us the direction. Question?
Why do grams and kilojoules cross each other out?
Grams and kilojoules don't cross each other out. Grams and grams cancel each other out.
Right, but you know how we go.
Grams and grams,
Right.
moles and moles, and the kilojoules get left.
That's what I meant today.
Yeah, so we end up with
The
kilojoules.
other way.
So 111 kilojoules are produced. Any questions? I'm not going to try to trick you with that words versus minus sign on an exam.
Well, I'll say produced.
Well, it will, like if this was a multiple choice question, and it was asking how much heat is produced, 111 kilojoules is the correct answer, that would be there. I would not put minus 111 kilojoules, because that's just being mean, right? Now, I maybe forget to divide by the 4 and stick that one in there. There might be some others that are negative, just to toss in some fun answers, but yeah. Questions? Yeah, got that one. Oof, end of chapter.